So we're starting the light chapter today from the 5054 syllabus. That is actually the biggest segment of the total waves chapter, but in my opinion, it's also very simple. There are very few formula that you need to take care for mathematical calculations, but there are certain concepts that you need to really understand properly to be able to solve the questions properly. One of the important part for the light chapter is how to draw the diagrams well. So certain measurements can be tricky in some cases, and drawing processes can be somewhat new. So I'm going to help you through that process as well. So let's get on with that. Light is defined as the combination of electric and magnetic fields that travels through vacuum at a speed of 10 to the 8 meter per second. Now, the detailed explanation for how the electromagnetic wave, or how light is actually electromagnetic wave, how electromagnetic wave actually exists to begin with, is not entertained in detail within your syllabus. But let me just put it this way. What we're going to see in our upcoming chapter in the discussion of magnetism is that whenever we have charge, let's say if we have a particle that this charge, let's say it's an electron minus E. Whenever charge particles move, we call it current. Whenever charge particles move, they produce a variation in the electric field around them. The variation of the electric field produces a subsequent magnetic field. So moving charges produce a magnetic field around them. Stationary charges do not. That's a very key thing to understand. If you have a stationary charge, it will only have an electric field around it, and that's it. But the moment you start to move that charge with respect to the observer, there will be a change in the electric field. That causes a magnetic field to come into existence. The moment the motion is stopped, the magnetic field vanishes up. So moving charges produces magnetic field, and they are definitely associated with an electric field as well. And steady charges or stationary charges only have electric field. So if we have a charged particle, maybe an electron or maybe a actually charged large object, metal ball or something like that, if we vibrate it back and forth in a motion, that actually creates an alternating electric field variation and magnetic field variation. This actually produces electromagnetic wave out of it, in which the electric fields and the magnetic fields are perpendicular to each other. It's actually quite difficult for me to draw how that looks like, but let me just show you a possible figure for making sense. So yeah, this is sort of like how it looks like in a three-dimensional space. The electric fields and magnetic fields are perpendicular to each other. So on one axis, for example, this is the y-axis, this is the z-axis, this is the z-axis, this is the y-axis, this is the x-axis. So on one axis we have the variation of the electric field. On a perpendicular axis we have the variation of the magnetic field. So it's somewhat shown like this. I mean, in many cases in many books you might come across figures that look like this. You have to visualize this as a three-dimensional figure. So figures like this may be helpful with the dotted lines or such, or figures like this might also be helpful. This one is actually pretty nice, a nice representation that we have the electric field on a vertical axis, and on the horizontal plane we have the magnetic field, which is represented by B for some reason, not by magnetic field M. And this is how electromagnetic waves go by. So whenever electromagnetic wave travels from one place to another place, whether it is passing through a medium or it is passing through vacuum, irrespective, it is created actually by a combination of alternating magnetic and electric fields. This is not a part of your discussion, but this is something that you need to understand, in my opinion, that you should know what electromagnetic waves are. Light is one part of the electromagnetic spectrum. Within the electromagnetic spectrum, we have actually quite a variation. Depending upon the frequency range, the scientists have divided the whole electromagnetic spectrum into 7 different parts. We have the visible light, which we call usually light. which has 7 colors in it, according to Sir Isaac Newton, who first differentiated the colors of white light while it passed through a prism in his laboratory. So we have this wave gear sequence where violet is the highest frequency component and red is the lowest frequency component. So this is the part to which our eye is sensitive to. We call it visible light. And above this range, we have ultraviolet, then we have X-ray, then we have gamma ray. So these are the frequency ranges above visible spectrum. And below red, we have infrared, then we have microwave, and then we have radio wave. These are the parts which are also invisible to our naked eye, these are the part which has lower frequency compared to this thing. One thing that you need to understand that I'm defining all of these individual part of the electromagnetic spectrum in terms of their frequencies, because like I have always been telling you, frequency of a wave is the basic property that defines a wave. Wavelength is not, speed is not. A certain wave's core identity is in its frequency. Whenever the wave travels, whenever the wave is created from the source, its frequency is determined depending upon the frequency of the source. So you have a source that is vibrating at a certain frequency. Wave is produced out of this. Wave is produced out of that source with that frequency, and that's it. There is no change of that frequency no matter what we do to this wave. If this wave is moving through some faster medium, it's going to have longer wavelength and longer and bigger speed. If it travels into a slower medium, is going to experience smaller speed and smaller wavelength, and those two things are going to change within a fixed ratio, but the frequency of the wave will always remain the same. So this is the part of the electromagnetic spectrum where over here we have higher frequencies. So higher, I'm going to just write higher F, and lower part is over here. This is a basic discussion for the light chapter. And then light also does some interesting physical happening, one of which is reflection, the other one is refraction, and it also undergoes a little bit of diffraction. And light, being a transverse wave, also shows polarization. So we're going to talk a little bit about polarization. And diffraction is also discussed by a very small fraction for your syllabus, but we have a bit more discussion about the refraction. The idea of reflection is very simple. Whenever light travels in a straight line, if it comes across a reflection surface, it is going to bounce off that surface following two rules. The first rule is that incident angle would be equals to, sorry, I mistakenly wrote greater than, incident angle would be equals to reflection angle. And the second rule is that three things: incident ray, reflected ray, and the normal drawn on the surface at the incident point, they all lie on the same plane, which means all of these three things, incident ray, reflected ray, and the normal, they are all going to be coplanar. So I'm not going to write that description over here, I just told you so. That's for the reflection part. And for the refraction, light follows one rule. The first rule that I'm going to say is the Snell's rule, is that whenever light travels from one medium into another medium, at the transition boundary, it undergoes a direction change in most cases. This change of direction happens due to the difference of light speed within those two mediums. So that actually causes the light to change direction. So whenever light goes from faster to slower medium, it bends towards the normal, and if it goes from slower into a faster medium, it bends away from the normal. So that is given by Snell's law. Snell's law actually gives us a fixed ratio, which is given by the ratio of the sine I of sine R. This is the more common expression for this constant, which can be also written as for the slide speed of the incoming medium. C is the general symbol for the speed of light. So, and C of the entering medium for the light. This ratio is equal for all cases. So if we even have multiple different variations of the incident angle, the refraction angle, we're going to always come up with the same ratio if we do sine A by sine R, and the ratio of the speeds either way. The second law is pretty much similar to the second law of reflection as well. It simply states that the incident ray, the refracted ray, and the normal drawn at the point of insertion, they all are coplanar. They are within the same plane. So in the reflection part, we actually have a lot to draw. I'm gonna show you some tricks to draw these things. We usually go by a lot by going for the mirror drawings. And whenever I'm about to talk to you about mirrors, one of the first thing that I should cover is what we understand by an image of a image produced by light rays. Image is basically a copy of the original object that appear to exist because of our view, that copy of the object is perceived by our memory. It is not actually physically copied, not a forested machine. Image is basically defined as I actually messed up the actual definition of image. Let me just find this out. A representation of the external form of a person or thing in art, no. The general impression that a person or organization or product presents to the public, no. The image of an object is the location where light rays from that object intersect upon reflecting from a mirror. Okay, that actually makes more of a sense, but it's not the complete definition of an image. So definition of an image in, do we have the Wikipedia definition? Wiki. In optics, an image is defined as a collection of focus points of light rays coming from an object. A real image is a collection of focus points actually made by converging rays, while a virtual image is a collection of focal points made by the extension of diverging rays. Actually, this one makes a more complete definition. So let me just clear this up. The way we find out the image of any point object, first of all, we're going to talk about point object, because any vivid object, it can be considered to be a collection of points. So if we know how to find out the image of a point by repeating the same process, we can also figure out the image of a bigger body as well. So using plane mirrors, finding out image is pretty simple. If we have a plane mirror, let's say something like this. Let's say this is a plane mirror, and we are asked to draw the image of this point over here onto the mirror. To find out the image, we need at least 2 rays. Why do we need at least 2 rays? Here's why. The idea of finding an image, I'm just showing you how the figure is usually to be drawn. The idea of finding out an image is that if we draw 2 random light rays out of the object's position, which fall onto the mirror, let's say these are 2 random light rays, by the law of reflection, they're both going to reflect it off at the incident point, producing equal angle. So let's say this is our first reflection where this angle and this angle are equal. And then let's say I should actually rub off this extra part. And this second ray, which is coming by, will also be reflected off like that of the mirror, where it also makes equal angle with the perpendicular. So these 2 light rays are going to become diverged as well. So because this is our object for which we want to draw the image, the light rays are going to fall onto the mirror, and after falling onto the mirror, they're going to be reflected back with equal angle. So the idea is that because these 2 light rays before falling onto the mirror, they were divergent, after reflecting off a plane mirror, they'll still remain divergent. This is just similar to transformation of a straight line about an axis or about another straight line, what you've learned in your mathematics class. So the way we can find out the image is that if we extend these 2 reflected light rays backwards, they're gonna actually eventually meet at a certain point. And it is that cross point of these 2 extensions of these reflected light rays is what makes the image. In this case, the light rays actually did not travel behind the mirror. Rather, we had to extend these lines artificially behind the mirror to find out this possible cross point. This is why we call this point a virtual image. So in essence, cases where light rays coming off an object would physically become divergent, and to find out a possible cross point of all of those reflected light rays or refracted light rays, we have to extend them backwards to find out an imaginary cross point. Those are the images that we call virtual images. On the other hand, there are certain cases where light rays will be actually converged towards a single point and they will meet each other. Those are points which we are going to call real images. Now, the reason virtual image actually exists is because of the way our eye is trained to see things. So why do we see virtual image even though the object doesn't exist there? Why do we see it in the first place? This is the part where our brain comes in. Try to understand the way our eyes perceive the position or the presence of an object is by having light rays coming off of that object and eventually hitting into our retina, which is processed by some electromagnetic signals, goes into our brain, gets processed by the optical center of the brain, so on and so forth. But key requirement is from a certain location or from a certain point on an object's body, light rays should come towards our eyes and it should enter in our eyes and we should receive that light rays. And that's how our vision works. So if we are not told that where this light is coming by, our eye will naturally perceive that object is in front of our eyes. So let's say one of the example that I can give you, let's say there is this is a human eye. Let's say, for example, this is a human eye. Here is the pupil and everything. So let's say here is an object. We have this object right over here, and light rays are coming out from this object into our eye, passing through the lens, and eventually entering into our eye, and eventually falling onto the retina, and we're able to see it. If we were not told that this object was over there, rather, if an alternative mechanism was developed, for example, let's say if we did place a mirror over here, and this object was actually put up right over here, and light rays would be coming to our eye, having a reflection in this pattern. If that happened, in that case also, our eye would feel as if this object is behind this mirror right over here, because this is how our vision works. We receive the light rays in a certain direction, our brain creates the image of that object, or it actually perceives the object position in the very same straight line in which the light rays are coming by. So actually I should draw the arrows backwards. Light rays are entering into the eyes, not coming out. We are not dealing with Superman. So that's how our vision works. So that's where the virtual image comes by, that because the light rays before entering into the eyes were coming in an almost horizontal direction, our eye will perceive the object to be exist in the same horizontal direction like that. So even though the object is really over here, our eyes would see this object right over here. That's the whole point why virtual images do exist, that our brain creates the position of that image by vision in that point. So any one of us who is regularly seeing objects would see this object to be over here because of the reflection of the light rays of the plane mirror. That's the whole idea for virtual images. So this is basically what happens for a virtual image, and this is sort of the mathematical way, or the opined way to draw the image for a point object using a plane mirror. This method works just fine, but this method can prove to be quite difficult for accomplishment, because in this case you have to draw some perfect angles over here, measure those angles perfectly, which is quite difficult because our protractors are only calibrated for 1 degree separation. So measuring an angle absolutely perfectly is actually quite difficult. And then you have to draw an angle on the other side of exactly equal number, and you should have this straight line. So within this part, there are a lot of different locations you can make a physical human mistake. Drawing the perpendicular properly can be your first source of mistake. Measuring this angle can be a second source of mistake. Drawing up this second angle can be a third source of mistake. So within drawing one I equals to r angle, there is possibility for making 3 mistakes. Equally goes for the second ray as well. Whenever we'll be putting them backwards, it is quite unlikely that this image would actually be placed in the exact position where it is supposed to exist. So this method would work fine if we can do the drawing perfectly, but in most cases it is actually quite difficult. So to avoid that difficult process, we can take help of some of the properties of images produced in a plane mirror, for the ease of drawing. So let's just discuss that part. What are the properties of plane error images? Number one, they are virtual and upright. So which means physical letters do not cross, and upright means their orientation would be exactly same. So top of the object would be in the same horizontal level. The second property is that same size image. The third, same distance away from mirror as object. The sequence actually doesn't matter as object. You can have them rewrite at different sequence. Number four, adjoining lines with object intersects mirror at right angles. And number five, less bright. These are the five that I can recall for the timing. There might be another one or another two. So I'm just writing 6 over here. If anything else shows up, we're gonna fill this up. But to make the drawing process easier, we actually take help of these two properties, this one and this one. What these two properties say, that the image should be equal distance away from the mirror as the object, and also if we join up the image and the object, which that line should cut the mirror at perfectly 90 degree. Which means in other case, in a secondary figure, let's say we are trying to draw that same figure, but the question has given us this is the mirror position, this is the object position, let's say over here, and they have labeled the mirror like this, and the question is asking us to draw the position of the image on the right side of the mirror using the help of geometry. So the easier way can look like this. So this is the given question to you. So what you are supposed to do, I'm showing it by red. So the first thing we can do, we can hold up our protractor and draw up a perfectly vertical line onto this thing. You can actually physically draw this line, or you can draw this line in a dotted line fashion, no big deal. Then you measure up how much is this length, and using a ruler, you give a dot at equally far away length onto this point over here. Doing this much would automatically define your image position. So you don't actually have to rely upon the accuracy of the reflected rays to actually find out this position. So you're not going to draw these second brackets or curly brackets. So I'm just going to erase those curly brackets. So you can draw this straight line. Drawing of this straight line is not a big deal. You can keep this in your figure, or if you don't want to keep this in your figure, no big deal. You can just do it by, you can represent this line by a dotted line to represent to the examiner that you used it as a reference for your figure, which the examiners do not mind to see. Rather, it's helpful for the examiners to understand that you know what you are doing. And then we simply go ahead and complete the figure with the necessary steps. What are those necessary steps? We draw up two rays from the object position onto the mirror. Any two position is good. So you draw two rays like that. And then you hold up your ruler against this intersection point and the image position. So you hold up your ruler against these 2 points and draw the first reflected ray, and repeat the process for the same second point. Hold up your ruler against the intersection point and the image and draw it up like that. So you pretty much have the reflections already. So give appropriate arrows. Light rays are coming from the object. Label the image I. The figure is not done because you just do this process not in the exact geometric way. Rather, you use the properties of the image to find this out. So you have to complete this figure by showing the examiner how they should be done. So you have to show the relevant normals over here, and also just for the sake of completeness, draw up the angle signs to represent which angles are equal. So I usually go by this one, that these two angles are equal by single angle sign, and these two angles, this pair should be equal by drawing double angle lines. This is going to complete our figure just by Just in case, in some figures, they appreciate to have an eye over here. So you can drop a pretty bulky eye over here. So draw this thing, make this thing black. And for extra precaution, label eye, which works. So that's how we can go for the image position. This was applicable for the point image. If we want to draw the image for a vivid object or for a large object, it's pretty simple. Let's say for a large object, let's say an object was given of this much length. This was an object. Let's say this is the tip of the object and this is the bottom of the object. So tip of the object usually has an arrow over here. The idea is very simple. In this case, you have to find out the image position of the O point. This is I, and then you have to do the same thing for the image of the A point. Let's say that position is B. So you're gonna have an image that looks like this. You just have to draw two more arrows, two more set of light rays over here to find out the tip of the object, which is I, and to find out the image of the bottom of the object, which is B. You should not draw this arrow. Actually, I messed up this. This arrow should not exist. Only this point should be there. And drawing up two more set of arrays, for example, like that, and this two goes by this, and you have this one attached over here, this one attached over here. Just like that, you can get the image of a vivid object. Usually, it's quite rare for the examiners to ask you to draw the full image for a single vivid object, because there can be so many overlapping lines. But asking to draw the image for one single point for a plane mirror is actually quite common. So that's one thing. The other thing that we need to understand that what kind of images can we have? Images can be of basically two types. We can have the actual crossing of the light rays, which we call the real images, and we can have the extended cross, or the virtual cross, or the non-real crossing of the light rays, which is done by extending the light rays backwards. That can also happen, which we call the virtual, for which we get the virtual images. Now, important for you to understand that real images are always inverted and virtual images are always upright. These two pair properties always come in pairs. So if I try to write this thing, let me just write this thing, that image description, or should I write properties? I think description is a better word here. So to describe an image, we need to first state what type of image do we have. And this type of image consists of two information at the same time. Either they are virtual and upright, or they are real and inverted. Number two property that we use to describe the image is where is it located. And number three that we use to describe is size. Size in this case actually means magnification, which means is it equal to the size of the object, bigger than the object, or smaller than the object. So these are the three properties, or these are the three information that is used to describe one image completely. These three things can come very helpful or can come very useful whenever we're going to go for the lens figures, so which I'm going to show you after a while. For the case of a plane mirror, the where is actually very simple. For the case of a plane mirror, we always write equal distance away from the object in a straight line behind the mirror, where the line cuts the mirror at 90 degrees, or you can say in a perpendicular line right behind the mirror at equal distance away from the mirror. So that basically gives you the where location. And plane mirror objects are always the same size as the object, but it is always less bright. This is the part that I did not discuss. The image is always less bright than the object itself, because whenever light rays come out of an object, we actually have the light rays spread out in radial direction. A small fraction of the light is actually used to produce the image on this mirror right over here. So that's why, and also some amount of light is actually some amount of light actually gets absorbed on the reflection surface right over here. So images produced on a plane mirror will always be less bright compared to the object itself, which means if we are looking at the object directly, we would definitely see a more brighter thing. So that's pretty much it for the image description. and the part for the reflection as well. If you go for the refraction part of the light rays, there is a simple formula that I would like to discuss for you to understand. That is the Snell's law, which in many cases can prove to be slightly difficult to apply. So just for the sake of easy understanding, I'm going to just show off this figure. Let's say this is our faster medium, and this is our slower medium. And a certain light ray is about to enter from the faster into a slower medium. So let's say this is the normal. A light ray comes in from this angle, and it means that if this slower medium did not exist right over here, is it same when we just put up a light source towards the mirror? Yes. Even if we put up a light source against the mirror, the image would still be less bright. Let me just explain it to you. Let's say, let me just draw it for you. I think it would make better sense. Let's say we have a mirror over here. We have put up a light source right over here. Let's say this is a certain light source. What you need to understand that if you consider that the light actually is coming out of the source and it's actually getting spread out in all directions, it's not a single directional light. So whenever we are going to place the image over here, so plane mirror over here, and if you're seeing it from this position, light rays are going to be reflected off this mirror and eventually reaching into our eyes. That's going to cause us to see the light source somewhere over here. So you need to understand that a significant portion of the light rays which are getting reflected off the boundary is actually coming to our eyes, but not all the light rays which is falling onto this surface. Because whenever light rays fall through any surface, there can be three different things that can happen. So let me just show you another figure. Let's say this is a surface, and this is medium X, this is medium Y. Let's say we have an incident light ray. Let's say the amount of energy within this incident light ray is 100%. Whenever light ray comes in, three things can happen. This surface can absorb some energy. Let's say that absorption is given as A%. And some light rays can go reflected off. So this is bounced. So I'm going to say B%. So I'm not using R because the third part is some of this light can get refracted through. So let's say that part is the transmitted wave. So let's say this is T%. So this T part will always make up 100%. Now, if medium Y is not transparent, then this T% can be 0, which means you are always going to have A and B. Whenever light rays fall onto some surface, some amount of light or some amount of energy will always be absorbed within the surface, and the remaining portion will be reflected off. Now, how much should be the reflection? How much should be the absorption? Depends on the surface. For example, plane mirrors do a significantly large amount of reflection, and they do regular reflection, and that's why we can see our images in that. Whereas rough surfaces or uneven surfaces, black surfaces do more of a absorption than reflection, so we do not see that much thing. This actually means that if we looked at this source directly at the same, let's say whenever the image of this light source would be produced in this mirror, our eye would be this much far away from the source. So the distance from our eye to the source is this much. So let's say that distance is maybe, let's say 1 meter. Now, hypothetically speaking, if the mirror did not exist over here, let's say the mirror doesn't exist and we are actually standing, let's say exactly 1 meter away from the mirror somewhere over here. So if we are looking at this source exactly with the same amount of distance, let's say 1 meter, which is going to look brighter? Should the image look brighter? Should the source look brighter for this view, or should they look equally bright, or the other way around? The answer is the image will always look less bright even when they are looked from the same distance away, because the reflection surface does always absorb some amount of light energy. Does that answer your question?
Yes, sir, it does.
বুঝা গেছে clearly?
জি স্যার, বুঝেছি। Thank you.
Acha, give me a moment. I just have to look up something. Okay. So the typical difficulty the students face whenever they try to go to solve some of this problem regarding the reaction medium, refraction cases can be for the choice of angle. So I'm going to explain this to you in part by part. Let's say the light ray is coming by, and this is the transition line in which we have the two medium, fast and slow medium, are divided by. If the slow medium did not exist, then this light ray is supposed to go in this straight line. This was supposed to be the original path, but because of the presence of the slow medium at this location, this light ray is going to bend closer to the normal. So that's what we mean by this thing. So it is actually bending closer to the medium. Not the, so that's the idea of what do we mean by closer to the medium or farther away from the medium. Now we don't need this extra line over here, so I'm going to erase that off. But I just wanted to show you what does it mean by further away from the medium and closer from the medium. So let me just erase that. Okay, so light rays are falling by in this fashion. Let's say I'm going to label this angle as X, label this angle as Y. Now we know that the refractive index is usually given by this formula, sine I over sine R. Oh, I should also represent the speed of the light. Let's say the speed of the light within this medium is Cx, and speed of the light in this medium is Cy. So this would be given by Cx by Cy. Now, what you need to understand, whenever we represent the case for the refractive index, there is a way to express the refractive index in its definition or in its terminology, so that we do understand from which medium the light is coming by, from which medium the light is within which the medium into which medium the light is entering. That's a really important factor. For example, if I want to represent this thing for this medium, for my drawn case, the light is coming from the faster medium, it is going into the slower medium. If I want to name this medium, let's say this is medium A, this is medium B. So I'd say this refractive index, if I want to write this refractive index of medium B with respect to medium A, that is going to be given by this way. This is going to be sine X by sine Y equals to Cx by Cy. So this is a refractive index of medium B with respect of medium A. Now in your syllabus, you don't have these subscripts over here. So in some cases, this might be actually not given to your level, but I'm showing it to you to make sense that refractive index of medium B is written on the right, and this is the light, this is the medium into which the light is entering, and refractive index of medium A is written on the left. Now let's consider a different scenario. This would actually mean that we put the light source right up in this medium, and the light was allowed to flow from medium A into medium B. If we revert the scenario, what if we put the light source into medium B following the exact same angle as over here and make it fall over here? By the idea of symmetry, whenever the light ray is going to enter from medium B into medium A, if the light ray was traveling in this manner, it's going to fall onto the same point, and it's going to travel in the same straight line as is, which means in this case, Y is going to be our incident angle and X can be our refraction angle. So even for that scenario, we can write that the refractive index of medium A with respect to medium B can be given by sine Y divided by sine X, which can be also represented by as Cy by Cx. This is the key part that I need you to understand. আমরা যেই মিডিয়ামের রিফ্র্যাক্টিভ ইনডেক্স বের করব, সেই মিডিয়ামের রিলেভেন্ট অ্যাঙ্গেলটা সবসময় নিচে আসবে। সো ইফ ইউ আর ট্রাইং টু গো ফর দ্য রিফ্র্যাক্টিভ ইনডেক্স অফ মিডিয়াম বি এর ভেতরে যে অ্যাঙ্গেলটা আছে, মিডিয়াম বি এর ভেতরে আছে হচ্ছে ওয়াই অ্যাঙ্গেল, সেই অ্যাঙ্গেলটা আসবে নিচে। মিডিয়াম বি এর লাইট স্পিড হচ্ছে Cy, সেই স্পিডটা আসছে ডিনোমিনেটরে। দিস ইজ দ্য কি পার্ট দ্যাট ইউ নিড টু আন্ডারস্ট্যান্ড। সো ইফ দিস ওয়াজ এয়ার and this was glass, if you're trying to measure the refractive index of glass, then this is going to be sine X by sine Y and Cx by Cy. If we're on the other hand want to measure the refractive index of air with respect to glass, in which case the light is considered to travel from within the glass into the air medium, then we should write the same formula as sine Y divided by sine X. So J medium refractive index, J medium relevant angle, relevant light speed, jabe denominator side, and that's the way we can do this thing. This is the easiest way to remember the formula and not to mess up the values, because sometimes it can actually happen. They can give you multiple different figures, and you might be given some angles and asked to do the calculation. The figure can actually be given in a reverted way. For example, they can give you a scenario where the light is going from air into glass, sorry, glass into air, but they might ask you to find out the refractive index of the glass itself. Now you should remember, if you're trying to find out the refractive index of glass, you should always do it by sign of other medium on the top and the sign of the angle of the glass medium at the bottom. This is the key part. So if you follow this method, you would not be mistaken in any case, but try to do that. If you get stuck anywhere, if this idea doesn't apply in some cases, I would like to hear about it. I hope it doesn't happen, because it's not supposed to happen. But then again, this is the easiest way that I know to distinguish between the expression of the formula. The next thing within the reflection chapter is what we have is called the critical angle. The critical angle is actually a pretty interesting concept. The idea is that whenever light ray travels from, actually I can pick up one of the images from the net where we can have a bit more straight lines. Yeah, this is a good image. So let's have a look over here, critical angle. Have a look over here. We are given three different scenarios. N1 equals to refractive index of the denser medium, N2 equals to refractive index of the rarer medium, theta 1 equals angle of incidence, theta 2 equals to angle of refraction, and theta c equals to critical angle. So let's just try to understand what is happening. You don't actually have to know this exact formula. This is actually another expression for the Snell's law, but you do not need to understand this whole thing, arc sine n2 by n1. Arc sine actually means sine inverse. This is also actually one other application of the Snell's law. You might actually know this thing, but you don't have to remember this formula differently. I want you to consider on the figures exclusively what is being shown over here. Whenever light is traveling from a denser to a rarer medium, or you can say from a slower into a faster medium, light rays will naturally bend away from the normal. So over here, we are seeing that we are having this light ray entering over here, and we have a bigger refraction angle. So theta 1 is small and theta 2 is larger. So if we start to increase this angle, which means if we keep the aiming point same, but slowly move the light source to produce this angle inside the denser medium or inside the slower medium bigger, as we are going to slowly increase this incident angle, this light ray is going to slowly fall closer to the surface, closer to the different surface. And eventually there will come a certain point that for a certain value of the incident angle, the light ray is going to travel perfectly aligned with the surface. What do we call this surface? I think it's called the বাংলাতে এটা বলে বিভেদ তল, ইংলিশে কি বলে? Boundary. It's called the boundary. Yes, I forgot the word. So in this case, the light ray is actually going to become aligned with the boundary of the two medium. So this is the case for which the refraction angle becomes 90 degrees, or you can say the refracted ray goes along the boundary. This is the scenario for which the light ray has the most amount of refraction. Because here's the deal that you need to understand. For the refraction to happen, light ray has to travel from one medium to another medium. So what is happening over here? The light ray has actually traveled from the denser into the rarer medium, but as it traveled into the rarer medium, it bent by 90 degrees, which means it is going along the boundary. So we have the effect of refraction over here. So the incident angle inside the denser medium for which this thing happens. So the definition of critical angle goes like this. I'm going to put it slowly, so try to understand this thing. Whenever light ray is entering from a denser into a rarer medium, rarer, or you can write lighter, or you can also say whenever light ray enters from a slower into a faster medium, the value of incident angle inside the denser medium, the value of incident angle inside the denser medium for which the refraction angle becomes 90 degrees. I'll say it again. The value of incident angle inside the denser medium for which the refraction angle becomes 90 degrees, or the reflected ray passes along the boundary of the two medium, is called critical angle. So this is the angle which is inside the denser medium, which we are calling the critical angle, for which the refraction angle would become 90°. So that's the idea of critical angle. Critical angle can be actually a very important factor, because this can help us to measure the refractive index of the denser medium much too easily. For example, if I say in this case the denser medium is D and then the rarer medium is R, so I can write that the refractive index of the denser medium can be given by sine 90 divided by sine theta c. In your syllabus, sometimes angle is also represented by only the letter c. It really doesn't matter, as long as you understand this is a critical angle, it's all good. So sine 90 has a value of 1, which ultimately gives us the refractive index of the denser medium is given by 1 upon sine of the critical angle. This actually can be proved to be much helpful to find out the value of critical angle for a lot of cases. And this same process can be used for the case of a lot of refractive experiment. Let me just show you one of those experiment setup. Experimental setup গুলো আমাদের ভালো করে বুঝা লাগবে, কারণ experimental setup গুলোর উপর থেকে আমাদের কোশ্চেন হয়. For example, this is one of the experimental setup for critical angle. Have a look at this image. What is happening? This is actually what we call a ray box. What we have inside is that we have a bright light source and we have a very small slit. So this is what I call a ray box. Actually, let me show you the figure of a ray box. So yeah, this is what a ray box actually looks like. These are actually a much too bigger setup. So there is actually a very large light source, and then there is a lens which makes the ray parallel by the idea of lens. That's how lenses work. And then we can place in small opening like this, which is going to work as a small slit through which a very thin thickness of light comes out. So if we do not apply this boundary, we're going to have the total light coming out. You can see that this light is still a bit divergent. Do you see that? This is slowly becoming larger. This is because positioning of the lens, which is responsible to make it perfectly linear, is actually can prove to be pretty difficult sometimes. So if we actually allow but if we allow a very small thickness of light, this is slowly going to become wider, but it's still workable for the purpose of the experiment. And then again, if we make it really thin, if the slit is really thin, then the light could actually become really less bright, so making the performance of the experiment pretty difficult. So there is actually a sweet spot, that how much bright light do you want, how much thickness of the light do you want, so at which the experiment is easily doable, and then the bending of the light or the splitting of the light is not so much to affect our experiment really badly. So those optimizations can be done, and most of the ray boxes actually have that process of optimization within themselves. So that's the idea of the ray box. So what was happening in this experiment is that this person put this ray box over here, and this beam of light is coming up, and they put the semicircular glass block over here. And what you should see, that in this case we are having total internal reflection. Total internal reflection means we are sending a certain light ray, and we can see that the light ray is actually reflected off of this boundary and eventually coming off. This can happen whenever the incident angle is bigger than the critical angle. Try to understand. For the critical angle, the reflected ray actually passes along the boundary. So if the incident angle is bigger than critical angle, the ray simply cannot enter into the secondary angle. It will completely bounce off of the boundary and eventually enter into the denser medium once again. This is what we call total internal reflection. We call it total internal reflection because the ray actually bounces off from the boundary of the denser medium. It doesn't even enter into the slower medium. And 100% light is reflected in this process. No light get absorbed, neither do they pass into the rarer medium. That's why we use the term total internal reflection. So the 100% light is reflected off, which actually gives the most bright reflection you can possibly get for any kind of reflection that you can think of. This is why this procedure is also used in optical fibers, where we can use consecutive total internal reflection to pass a single light ray from one end to another end without much decrease of the brightness of the light rays. Anyway, this was the case for total internal reflection experiment. For example, we have another scenario over here where we still have total internal reflection. So You can actually go into this YouTube video, but I would like to show you some more figures where Rayboxes are actually used. Did I not write experiment? Yes. Why don't I have? Okay, this experiment is actually done by a small piece of laser. So they are sending a bit of a laser light over here, which is giving us this whole view. So gelatin entry. So this is actually a gelatin something, which is a reflective medium basically. Do they not show the experiment of critical angle anywhere? I believe I saw one of these images. This is actually the case for the of the of the optical fiber. You send in the light at such an angle so that the light cannot actually leave out of this tube, and it is made to bounce off from many internal boundaries and eventually leave on the last edge. This is the key mechanism for optical fibers. This is the part that I was showing you a bit earlier, that light is one part of the light is reflected out, the other part is reflected off, and both of them are actually less bright compared to the earlier. I cannot see an actual view where the experiment Raybox. Should that give us some good images? So let's have a look at this YouTube video, because they are proposing a video over here. Might as well get.
In this experiment, we will find the critical angle of a
It'll take me.
semicircular perspex block. You will need a pen and paper, ruler and protractor, and a Raybox. The lens focuses the light from the bulb. The single slit aperture produces a narrow beam. The blanking plates prevent light from leaking from the sides. Plug the Raybox into a power source. Set it aside. In the middle of the page, trace around the perspex block. In the middle of this straight boundary, mark out a line that is 90 degrees to the boundary. This is known as the normal. To find the critical angle of the block, we must look at the ray from the denser medium to the less dense medium. In this,
one thing that I should mention, the reason we are doing this experiment in this way is that this is a perfectly round surface of half semicircular round surface. So they have aimed this light ray directly perpendicular to this point, so that the light enters from the air into the perspex, which is actually a glass, air enters from the air into the glass without any bending in the surface. The way they make sure of that is just by looking at the alignment of these two rays, because if that doesn't happen, we would be seeing some actual variation over here. So we are avoiding that just by making sure that the light falls onto this point in a perfect straight line. So that's why we are shooting the light from the curved surface, so that eventually the light is about to leave from the denser into the rarer medium, or from glass into air medium within this experiment.
In this case, we should observe the path going through the perspex, going through into the air. When the angle of incidence is smaller than the critical angle, the light is refracted into the air. When the angle of incidence is exactly equal to the critical angle, it travels along the boundary. But the moment that it becomes larger than the critical angle, the light is fully reflected. We call this total internal reflection. So to find the critical angle, we want the point just before total internal reflection. Mark a point on the incident ray, remove the block, join the cross up with the normal. The angle between the incident ray and the normal is the critical angle. Measure it using the protractor. So I've worked out the critical angle of my perspex prism is 43 degrees. Here's an extension to this experiment. Find the refractive index of perspex.
Okay, they actually did not show us the whole process. They just dictated that. Actually, I think it made sense. তোমাকে বুঝছো কি দেখাতে যাচ্ছিলাম?
জি স্যার।
Yes, sir.
আচ্ছা ঠিক আছে, সো দ্যাটস দ্যাট। এরপরে যে জিনিসটা আমাদের লাগবে সেটা হচ্ছে ক্রিটিক্যাল অ্যাঙ্গেল গেল, টোটাল রিফ্লেকশন গেল লাইট চ্যাপ্টারে, এছাড়া আর আছে হচ্ছে দেন উই হ্যাভ ডিরেক্টলি দ্য লেন্স চ্যাপ্টার। আচ্ছা, what do we have on the lens chapter? Acha, let me just get into the key components. Lens is considered a refractive medium, that is where at least one surface is curved. The key purpose of lens is to bend a group of light rays into an ordered fashion. That's the word, in an orderly fashion. So lens can either, so in many cases to describe the behavior of a lens, we as the input we consider parallel light beams, and we define the lens depending upon how that beam behaves after they pass through the lens. So if it so happens that we have a lens over here where a beam of parallel light falling onto the lens ultimately become closer to each other, which we call the converging behavior, then we're going to call this lens a converging lens, which usually looks like this, where the edges are thin and the center is bulk. And for some other lenses where the center is thin and the edges are bulk, the parallel light rays are actually bend outwards. They spread apart in such a way that if we extend them backwards, they're going to be appearing to spread out from a single point. This point of backward is what we call the focus for an diverging lens, and the actual point where the light rays cross for the case of a converging lens is what we call the focus point. So this is the very basic definition of the diverging and a converging lens. The way we can determine whether a lens is convergent or divergent, just by looking at the shape of the lens, is just you compare between the thicknesses, how the thickness is at the middle and how the thicknesses are on the edge. If we have a thick middle portion and thin edges, this is a converging lens. And if you have a thin center portion and you have thicker portions on the edges, this is a diverging lens. However, we can have a lot of different shapes for the converging lens and diverging lenses. This is what we call biconvex, where we have both the sides curved. This is what we call biconcave, where both the sides are hollowed. We can also have planoconvex, which looks like this. One side is perfectly flat, the other side is curved. We can also have concavoconvex, in which one side is hollowed out, but the other side is curved more. So this is that type of lens which is called concavoconvex. On the other hand, for the concave lenses, we can have planoconcave lenses, which look like this. One side is perfectly flat, the other side is hollowed out. And actually, I should erase this line. Okay. And then we can also have convexoconcave lens, where we have one side convex, but the other side is hollowed out more. So something of this shape. So what you should see over here, that the center is thinner and the edges are thicker. So that also makes it a diverging lens. This is the most common shape that is used for most spectacles, because majority of the people around the globe who have some eyesight problem has short-sighted eye, and short-sighted eye problem is basically happens whenever their optical lens is doing more converging compared to what they should do. So to correct that, we have to make the incoming rays to the eye a bit divergent. So this is the more, so we use a bit of a divergent lens. So other than using a divergent lens that looks like this, just to have a more human-like look, this is the most preferred form of lenses, spectacle lenses, that is used around the globe. So that's the very basic classification of the lens in terms of their shapes. How do we draw the lens figures? This is the key part. To draw any optical figure for lens, we need to draw two rays coming off the object, only two. How do we draw these two rays? That's a bit of a different issue, which I'm going to address just a little bit later. Number one ray is very simple. The one ray that passes through the optical center and goes undeflected. Now, there is a key part that I need all of you to understand, that for in many cases, not in many cases, in all cases of the lens diagrams that we're going to see and do, we're going to do an approximated figure. So we're not going to draw the total figure in all of its details, so that we're going to draw a much more easy to draw version of the figure. What I mean by this is can be I'm going to show you right over here. So let's say if we have a biconvex lens like that, if let's say this is what I call the principal axis. So this is the center line joining the two center points over here and over here. Now in an actual case, whenever a light ray falls, let's say if a light ray falls over here, it actually undergoes two refractions before it comes out on the other side. So whenever it is going over here, it is air from air into glass. So over here we're going to have one bending. Whenever it leaves out from the second surface, it goes from glass into air once again. So you're going to have another bending right over here. So at the two medium change surfaces, it actually undergoes two bending. And this is equally applicable for all the other rays as well. So they all go multiple bending, and eventually that's how they go through. The ray that falls perpendicular onto the surface doesn't go bending, but it does experience the speed variation. So it actually slows down through the glass medium, and then eventually as it leaves, it actually speeds up once again. It doesn't bend because the incident angle is 0 degree. For the sake of convenience, we don't usually draw these figures in this manner. Rather, what we prefer to do is we only show the bending at an imaginary from an imaginary line that lies within the aperture line of the lens. So let's say this is the principal axis of the lens. If we join these two corners of a lens, this is the line that we call the aperture line. In some cases, mostly in graphs, a lens can be only represented like with this line. So in many cases, if you have graphs, you might actually also come across this thing. Let's say you have a graph paper over here where the examiner wants you to draw something. And let's say within this graph, there is just a straight line. Can I not draw a straight line over here? Maybe not a perfect straight line, but a dotted line would do. So maybe the examiners are going to give you a vertical line like this and label this as LL prime and say this is the lens. So what they are trying to tell you is that there exists a lens over here where the curve of this lens could be anyhow, but we are not interested to show you the curve of the lens because you don't need that for your drawing. All that you need for your drawing is the central vertical line, because that's where we typically show the bending. So for the sake of convenience, what we do is we show the bending of the light rays entering into the lens, coming all the way up to this point, and then from this point we usually show one bending. This is done for the sake of easier drawing. This is not the actual way by which light rays actually bend. Light rays actually undergo two bends at two surfaces. This is something that is very important. The reason I bring that up is to give you the idea for optical center. The optical center of a certain lens is this point. Let me just show you. Okay, in this case, the light rays are really dimmed out, so not so good, not so good. Why is it so difficult to find an optical center figure? This is weird. There is a difference. So can everybody see this image? Like at least now? Full one. So try to understand.
Sir.
If we have a thick lens, what is going to happen? The incoming ray is going to have the optical lens is basically the point. This is the definition of optical lens is that if a light ray entering through a lens after exiting remains parallel to the original direction. So let's say this is the incoming direction of a certain light ray, and after exiting through the lens, if this transmitted ray or if this leaving ray is parallel with the incoming direction, if that logic is fulfilled, then the location or the dot at which this passing ray cuts across the principal axis inside the lens, right over here, this point where my mouse is, which is looking like a zoom in icon, this point is what we call the optical center. Now, whenever we have a thick lens, this bending is going to be significant. But if we have a thin lens, then this side shift would be very small. So what I'm trying to mean is something like this. So uh, let's say this is a lens. So if you have a very thick lens, then the optical center of location is gonna be, let's say, somewhat like that. So you're gonna have a line like this. Now if I make the lens really thin, let's say if the lens is made of only this much thickness, then this amount of so in this case we had this much shift between the two light rays path. They're both parallel, by definition they have to be parallel, but there was this much horizontal shift. There was actually this much shift in this case. Mean, okay, try to understand the difference between the two words bend and shift. Bend means actually getting in a different direction than the original way. So there is an angle between the original direction and the final direction. That's what we mean by bend. Shift means both the directions are same. So incoming directions and leaving directions are same or parallel. But if there is a shift, it means it is somewhat moved away, but it's not working in the same, in a different direction. It's still parallel, but working in two different paths. So what I mean is that whenever the lens is going to be thin, then this amount of shift is going to become much too smaller. So the original ray and the leaving ray, they're pretty much going to be pretty close to each other. So for the sake of simplicity, the way we work is that for your syllabus, all the lenses that we use for our experiments are considered to be thin lenses. And that's why the optical center is usually represented by a dot or by a location through which a light ray passes without any bending. So we do not show any bending whatsoever. Once again, the reason we do not show any bending, like I said, told you earlier, that if we are to show any bending, for the sake of simplicity, we only show the bending exactly on this line, which means if any light ray passes through this point, the bending should be shown at this point. But by definition, optical center is the location where the bending is not happening. So that's why we only show a straight line perfectly passing through the optical center without any bending whatsoever. So that's the idea for an optical center. And for thin lenses, we can use a single straight line representing the light ray. But if you want to understand this in a much deeper level, if you ask yourself that does the light ray really not shift at all? The light ray does shift a little bit, but we consider that amount of shift to be negligible for our experiment, and we discard that value for your O-levels level of experiments. But if you really want to get into optics and eventually go into much deeper calculations in your master's or in your PhD levels, you shouldn't discard that shift. That can be a very important source of error unless you take it into account. So the first ray that we have to consider is the ray that passes through the optical center and goes undifferentiated. This is the first ray you have to draw. The second ray is a bit tricky because for two type of lenses, we can have two type of rays. So I'm going to write this in words. Let's say for converging lenses, and right over here, I'm going to write it for diverging lenses. So ray
স্যার আপনি কি এটা মাউস দিয়ে লিখছেন?
না, মাউস দিয়ে না, আমার রাইট প্যাডে লিখতেছি।
ও আর স্যার একটু ক্লাস শেষ করে আপনার সাথে একটু কথা বলবো।
আচ্ছা, Okay, let me explain these two parts. For converging lenses, the second ray would be ray coming parallel to principal axis and leaving passing through principal axis focus, or ray coming through the principal focus and after leaving becoming parallel to the principal axis. We have to use any of these two rays. For diverging lenses is the same thing, only through principal focus would not be through principal focus. It would mean aiming at the principal focus, or it would mean leaving away from the principal focus, because for the diverging lenses the rays become diverted away, so they do not actually get closer to the principal focus, rather they actually move away from the principal focus. So I'm going to explain all of these four rays part by part. Let me just pick up some images from here. Yep. This is actually one of the nice figures. Actually, I can open image in new tab. Can I zoom in? Okay. So have a look at these three different rays that they have drawn. We don't have to draw all three, but we can choose any two of them. To be honest, one ray we have to draw. So let me just copy this image and bring it up over here. Might as well be helpful for the upcoming discussion. I'm going to paste it over here, zoom it over. Okay. So this is our ray number one. Let me use blue. This is our ray number one. We have to draw this. This doesn't have any alternative. So from the tip of the object, one ray that goes to the optical center, undeflected, and we have to extend this further till the point we get the image position. That's one ray. The second ray can be either this or this. So the first definition that I can give you, ray coming parallel to the principal axis and leaving, passing to the principal focus. So this ray is coming parallel with the principal axis. This is your principal axis. This dotted line is your principal axis. It is coming parallel with this one, and it's falling to that imaginary aperture line of this lens, which is basically this point, and then bending in such a way that on the right side it passes through the principal focus and then keeps on doing its journey. You have to draw either this line, or you can draw a line that comes from the tip of the object, goes to the principal focus, and falls onto the lens, and then after passing through the lens it becomes parallel to the principal axis. So ray coming through the principal focus and after leaving becoming parallel with the principal axis. So this is basically the same version. I mean, this is just the two opposite sides of a coin. So if it is coming parallel with the principal axis, after going to the lens it goes to the principal focus, or if it comes through the principal focus, after passing to the lens it becomes parallel. You have to choose either of these two for the converging lenses. For the divergent lenses, it's just the other way around. Let me just find out one figure for the divergent lens so that I can explain it to you. I don't have both of them. Yes, got it. Was I not looking for this one? Yes, I was looking for this one. Actually, how big is this image? Not so big. How big was this one? Yes, this is the one. Have a look at this one. I'm gonna keep this part over here so that I can explain to you what this conversion actually means. So have a look. If you're trying to find out the image for diverging lens, what we're gonna do? We have this diverging lens over here. We have this object over here. So in this case, this is the vivid object. We are trying to find out the image position of the tip, because if we know what the tip is, we can pretty much draw the remaining of the object onto the in between the principal axis, so that this whole object would have its image over this position. So finding out the location of the tip of the object is basically our aim here, so that we can draw a vertical line and make up the image very easily. So what the two lines are we getting at? First of all, this is our compulsory line. We have to draw this, the line that passes through the optical center and goes undeflected. Then we have the two options. First one, we can choose a ray that comes parallel with the principal axis. Let me use red for this one. That comes parallel with the principal axis, and as it leaves from the lens, it appears to be coming out, or it is as it appears to leave from the principal focus. So you can see this ray is coming by, it was parallel, and then it is as it is getting away from the original direction in such a way that if we extend this line backwards, it would be appearing to be coming off from the principal focus on the left side. So that's the point, leaving from. So ray coming parallel to the principal axis, and after going through the lens, it appears to be leaving from the principal focus on the earlier side. So এই পোর্শনের প্রিন্সিপাল ফোকাস থেকে বের হচ্ছে বলে মনে হবে। এটা হচ্ছে একটা, so this is can be our option number 2 এটা, or we can choose another one, the array that was coming from the object which was aiming to the principal focus on the other side. So this ray, have a look over here, you can choose also choose C. So if you choose C, AC is coming through the coming at an angle in such a way as if it was aiming towards the principal focus on this side, but as it passes through the lens, it becomes parallel with the principal axis. So here I'm using the term aiming at. So I'm going to describe this ray C in like this way: a ray that comes from the object aiming at the principal focus on the other side, and after passing to the lens, become parallel with the principal axis. So this is your alternate option 2. So one have to be drawn, it is a must, and you can either draw any of these two things. Important thing in this case, 1 and any of these two, or I mean 1 and 2 or 1 and 2, they are becoming divergent. So if you compare these two, or if you compare these two, they are becoming divergent, so they are not going to cross anywhere on the right side. So if we extend them backwards, we're going to find out this crossing point right over here. This is the virtual cross point of the two light rays because they are divergent, and that basically gives us the position of the image of the object, and that is why we have this virtual image over here. So এই হচ্ছে আমাদের রে ডায়াগ্রাম আঁকার বেসিক রিকোয়ারমেন্ট। ফার্স্ট রেটা খুব সিম্পল, সেকেন্ড রেটা টেকনিক্যালি আমাদের বুঝে রাখতে হবে। বিভিন্ন সময় বিভিন্ন ফিগার রে ইউজ করে, so if you don't understand this properly, sometimes you might actually come across some difficult problem. For example, what you're going to see for this figure, which we're going to discuss in our take up on in our next class, and I'll explain this figure in detail to all of you. For some reason, I'm not having a full image
এটা
of
আমরা
this one.
কেমনে বুঝবো যে কত ডিগ্রি অ্যাঙ্গেল আমরা বেন্ড করব?
We're not gonna measure the angle. We're gonna bend the light rays depending upon the position of the principal focus. Usually the principal focus location is given to you in the figure. They're going to tell you that how far the principal focus point is from the optical center of the lens. So you can, if the figure already have this point labeled, well and good. If it is not labeled, then you have to use your ruler to physically measure out the length and label the principal focus point. Then you can use the principal focus point to go ahead to complete your drawing.
বুঝছি।
Beautiful. So এই ফিগারটা আমরা নেক্সট ক্লাসে আলাপ করব। আমি জাস্ট একটু ইনিশিয়াল রিক্যাপ দেখাই নিচ্ছি। সেটা হচ্ছে, if you have a look over here for the first figure, they have used two different rays. Now over here you can see that one of the rays which is compulsory, that is the ray that goes to the that goes to the optical center, which is bound. But for the second ray, they didn't choose a light ray that came parallel to the principal focus. Rather, they preferred a light ray that passed through the principal focus, and then after passing through the principal focus, after it becomes parallel with the principal axis. That's the ray that used over here. So this is our ray number 1, this is our ray number 2. But if you go for all the other figures beneath, you'll find out they have used the first ray is common everywhere. For all the figures, we have a ray that passes to the principal, that passes to the optical center. But for all of these other figures, they have used as the second ray as the ray that is parallel to the principal axis and falls onto the lens. Parallel to the principal axis, falling onto the lens. Parallel to the principal axis, falling onto the lens. Parallel to the principal axis, falling onto the lens, and so on and so forth. So number 2 array can be a choice, and typically we could use either of them, but choosing a certain ray on a given scenario can give us some advantage in terms of drawing. in terms of an easier process of drawing. So that's basically why we have two different options and we have to understand both of them. Whenever you are going to be drawing figures, you don't have to draw all three. You have to draw definitely one if you are drawing, and between 1 and 2 you can choose anyone. For your syllabus volume, examiners really like the one that is the first one, ray coming parallel with the principal axis. For your physical drawing, in most cases you don't have to go for this one where the ray was passing through the principal focus or it was aiming at the principal focus. You don't need that for most cases, but if it's needed in some cases, we would be definitely open to use that for the requirement of that question. এই পর্যন্ত বুঝা গেছে কিনা?
জি স্যার।
স্যার বুঝে গিয়েছে।
ঠিক আছে, আজকে এটুকু থাক। ইনশাআল্লাহ আমরা আমাদের পরের ক্লাস কালকে না?
হ্যাঁ স্যার।
হ্যাঁ, কালকে ইনশাআল্লাহ আমি এইটার বাকিটুকু আলাপ করব, তারপর দরকার হলে আমরা ওয়ার্কশিটে কিছু প্রবলেম সলভ করলাম। থ্যাংক ইউ ভেরি মাচ। নুহান, তোমার সাথে একটু পরে কথা বলতেছি। আসসালামু আলাইকুম।